Hey everyone, welcome back to part two for this week. And I wanted to share this one because I love coming across titles that make you first go, what? Somebody really studied that? How's that possible? And that's what's fun about epidemiologic methods. So in this particular study here, this group was comparing individuals who consumed nuts during pregnancy versus those who didn't, and then looking at age 5 to see about potential peer-related problems. And so I think they defined here as, um, child development related behavioral development stuff. And so why age 5? Well, maybe that is an age where in Japan it's very common to do assessments. I don't know. I'd have to read the article again to evaluate that. This was not a prospective study, so they weren't collecting a cohort of women and then following them for 5 years, but they were looking at their historical reports of nut consumption and then looking to see if there was differences in behavioral development between the two groups. So again, it's just kind of a fascinating thing, and I share it to kind of expand your thinking about what is possible within your world. What is possible within your practice? Okay, now, we left off with calculating rates in open epis. Pretty simple. We saw that. We're going to see how simple it is to do relative risk and the odds ratio now. And I'm going to do things in this side by side. I think this might be easy to kind of visualize everything. So if we click on 2 by 2 table, and then we click on enter new data, then what we're going to do is highlight if somebody has the disease or doesn't have the disease. And we're going to then place them based upon exposure. So this is the at-risk group, the positive, and this is the reference group, the negative. So here, let's go with 4 people got the disease that were in the high-risk or at-risk group or the exposed group. Let's say that 2 people in the group did not get it. So it's a very small group. It's just 6 people were in our at-risk group, how we define them. And then 11 people got injured in the lesser risk or reference group. So you're like, first, like, wow, that's more people, but it's out of a total of 76. So we're looking at proportions here, 4 out of 6 versus 11 out of 76. So now let's calculate. So we calculate and we see lots of blue. If we go with conservatively the two-tail p-value, we're at the 0.01. If we round it up, 0.01 level there. Next up, let's take a look at our risk ratio. The risk ratio is the name for the relative risk. And there's other stuff up here too we can take a look at, like the risk and the exposed. We saw 4 out of 6, so 66.67%. So it gives us some nice percentage numbers we could report if we wanted to. But our risk ratio here, 4.6, meaning those in the at-risk group were 4.6 times more likely to get injured than those in the reference group. And we see our confidence interval. And again, they are in blue there or purple there to illustrate that it was significant. Now, when doing a 2 by 2 table, the OpenEpi gives you the odds ratio. Let me blow this up for just a second. Right, there's our 4.6, and if we go over and look at my data over here from the volleyball study, 4.6, I'm reporting 2.1 to 10.1 for my 95% confidence interval. In comparison to the referent group there, so we saw that 6, right? 67% of all injuries in that group. And of course, given a little asterisk there to then cue you down to the end of at the bottom of the table there to see what the significance level was. So that's how it was reported in that paper. The odds ratio is also presented. Now, that's what's nice about doing a 2 by 2 table is you can get the odds ratio here. How else is another way to get the odds ratio? Doing logistic regression or univariate regression. any type of regression that can get you the odds ratio. Odds ratio is easy to calculate here in the 2x2 table in this case, but if we had multiple additional variables we were looking at, we would want to then explore it with a regression. Now, which one would you use? Odds ratio? Yeah, it doesn't really matter. Sometimes the editors may choose one. They may suggest using one odds ratio versus the other odds ratio. Both of them here, 11 point something. Why is the odds ratio so much more than the risk ratio? Well, that gets back to how things are calculated. Remember, there's differences in the cell calculation. You'd have to go back and look at those slides to see how that's done. One thing you need to be aware of is if you're to use an odds ratio, the odds ratio, when you've got a small sample size, and so this sample size was 82 overall, the odds ratio will really kind of overestimate the risk magnitude in comparison to the risk ratio. Now, I could have reported the odds ratio. It's not uncommon that people do that. It's preferred for a cohort study to do the risk ratio in this particular situation. If I was doing some adjusting for different variables, I would want to then consider an odds ratio, but I didn't do the odds ratio because it probably would be this over magnification. Confidence intervals, again, what's important when looking at the confidence interval is, and you probably learned this in another biostatistics class, that if the 95% confidence interval crosses 1.0, then it by definition is not going to be significant. So we see in all these examples here that they don't cross 1.0, thus they're significant. So regression here, regression models, these are important tools used in epidemiologic research, and they can be beneficial when looking at a lot of different factors. This is something we're not going to explore or do examples in this class. Probably, from what I understand, it's something you've done in other biostatistics classes. And Intellectus, I know, is your primary software. I'm more knowledgeable with SPSS. If you were to ever pursue an epidemiologic study design, then that's something easy to figure out at a later time, because Rocky Mountain, I know, has a very nice video library showing how to do different statistical analyses. Okay, let's talk about the receiver operator characteristic curve. And I'm going to blow this up now because we're not going to be using OpenEpi anymore. So the ROC curve. The ROC curve is a method to express the relationship between sensitivity and specificity. So what you're ultimately doing is constructing or plotting a true positive rate against a false positive rate. Now, in this study example that I've given in the past here, have this made up quadricep to hamstring ratio. So that's what we are using this ratio to categorize people into one of two groups. Well, how did we come up with whatever that ratio is? Now, I don't define what that ratio there is. Is it 3 to 1, 2 to 3? Who knows? It's not important for the example, but let's say the ratio was something where it's like 0.75. How do we come up with 0.75? Well, we ultimately would use a ROC curve to help us figure that out. And with the ROC curve, again, SPSS, easy to perform. I'm sure in Intellectus there's an easy way to do it too. Basically, what we're trying to do is to plot a number that is in this higher left corner area here. So that represents a test with high sensitivity with little or no loss in specificity. What we don't want is one against the line here like this. Now, if we had one that was reversed and curved down here, well, that could be fine too. We're just going to have to flip things around when we do our data analysis. But ultimately, we're wanting this here because this is illustrating to us that there's a certain number that's associated with the injuries or the events that we're looking at. And so when we plot the rock curve, what we would do is go, okay, right about there. That seems to be like the most, the one that's furthest to the left here. So I'm going to be looking in my readout for something that's around 90 or so and something that's around 20, or 100 minus 20, so 80. So an ideal test again, which that'd be amazing if you had that. Oftentimes actual tests are like that. No predictive value if it's right along the line. So if you're doing something in SPSS, here's like an example where you've got your test variable. This is where I've got a series of numbers illustrating a particular jump test on a force plate. And then I'm plotting it against injuries during the season. So it's plotting and looking at, okay, well, what is the injury incidence like compared to test performance scores? And then in this particular one, I would predict that a smaller test score indicates a more positive test, means people are at a greater risk of injury. So this is where you would kind of manipulate that. If you thought a larger test would indicate a more positive test, you would click it there. And then you're going to get a printout. So talking about the area under the curve, this area under the curve here. And what people look at is you get, sometimes people will report this area under the curve. Ideally, what they're wanting to see is something that has a 0.05, something that presents as significant. Now, not always the case that's needed, but I think that's what's wanted. And so, again, here is an ideal situation. Here is one from a paper that I did where it's like, okay, very weird presentation there, basically worthless, but then there's this component right out here. So I chose that spot. So I was looking at something that was in the 0.9 range and the 1 minus 0.55 range. So here it is kind of blown up a little bit bigger. So again, it's kind of like worthless, not predictive, but there was this spot here that really helped to dichotomize the groups into two. So here's at that 0.912. If we're looking at things back here, again, if we're up in this area here and that arrow's not in the way going across, we're in that 0.9 area. So what I'm looking for is something that maximizes, let me rephrase that. That's probably closer to 0.875. Yeah. So if I move that out of the way, coming through here, yeah, that's closer to 0.875. I misspoke there. My apologies. So I'm coming across 0.875 because what I want to do is I want to find something that maximizes sensitivity here and then minimizes this as much as possible. This is the number related to my test. So if I go back here again, all right, so that's around 0.875 there coming down. All right, that's around, that makes sense, kind of 0.57 area there, 0.58. What did it say? 0.875, 0.57, 0.58. So you're looking for a number here, and now this is going to be my cutoff score. So that's how I use this to categorize people into one of two groups. So the rock curve can be effective that way. What are other ways? Well, you could just categorize people based upon what people believe to be a risk factor. Let's say you're doing something for running and you believe the presence of a certain angle at the foot is associated with a greater risk of injury. You could make that then be your risk factor cutoff, even though maybe it's never been explored before. I knew a guy that did Q angle at the knee. So for those of you who aren't familiar with the Q angle, it's a relationship between, an angle of the patella and the hip and a measurement you create there, and having a greater Q angle is probably less ideal. So somebody took a look at that and found a particular range that was associated with a greater risk of injury. It hadn't been done before. They did not do a rock curve. They just kind of categorized people like 0 to 5, 5 to 10, 10 to 15. And I think you saw that paper a week or two ago. So that's how they did that. So now what I did is I broke people up into at-risk and lesser risk groups. So 0.9125, that was if you were 0.1925 or less, you were the at-risk group. If you were 0.9126 or more, a bigger number being something that was better, then you were in the reference group. And if we go across here, we see that there were 14 injuries in that group versus 2 in the other group, and that was 4.2 times more likely to be injured, significant 0.024. So what's my point again? Well, ideally, a rock curve is going to have this presentation to it, but when you have something like this, it's worthwhile to explore it. All right, some additional stats. Kaplan-Meier survival statistics. These are used to display survival data. So this particular one here, when they talk about survival statistics, oftentimes they're used for identifying time to death. Like after somebody's had a cancer diagnosis, what's the time to death, one treatment versus the other treatment. This particular presentation here, this was comparing the speed on an agility drill test and looking at time to injury. So this kind of gives like a qualitative presentation to it. You're looking at it, it's like, okay, there's maybe not that much of a difference. Maybe the faster people, well, this is interesting. The faster people, the first person got hurt right off the bat, like within a few days. And then the next one didn't get hurt till a few days later, and then a few days later. Whereas the slower person, it took longer. So this is kind of a worthless, this is one of mine, this is kind of a worthless one. It doesn't really tell you anything about how early into the season that somebody was getting hurt. Here's one from Mark Paterno. He's a physical therapist, does a lot of research in ACL injuries. And what's valuable from here, he's able to, in this Kaplan-Meier survival curve, illustrate the occurrence of second ACL injury and basically highlighting what percentage of people had an injury, a recurrence by their 20th athletic exposure. And so showing, because there's this steeper drop here in those people that were the ACL reconstruction group, they had more ACL injuries, second ones, versus the ACL injury rate in a control group. Just shows that there's a problem here where maybe people aren't getting rehabbed as well or aren't ready to return to sport. And so it highlights a potential problem. So there is a valuable qualitative role to those types of things. Sensitivity and specificity, I'm sure you've seen this before. There's some valuable ways we can think about sensitivity and specificity with our epidemiologic studies, and that gets into the spin and the snouts. Sensitivity here, thinking about the snout, and specificity, the spin. So how could this be valuable? Well, let's take a look at some data here. So this data, a population of 92 college athletes. There were 5 injuries in each group, but you can see the proportions were really different. And so the sensitivity and specificity, you can calculate that. So you can think about this as a quote unquote test. How good is this as a test for helping you understand the risk somebody is in? Specificity. What's specificity mean? Well, spin. When a test has high specificity, a positive test results in the need to rule in the diagnosis. So this is something that people think about. So, okay, let's say somebody had a positive test, means that they had poor scores on all 4 tests. Well, there was a total of 14 people that had poor scores on all 4 tests. Only 5 of them got hurt. Would all people potentially benefit from interventions to reduce the risk of injury? Possibly. Low risk, right? What if it was something else that required surgery? Then maybe you've got a different idea going on. But in this particular case, using specificity, positive test, you might suggest to that person that they might be at a higher risk for injury based upon their presentation. And if this was their presentation here where they were slower on an agility drill test and had lower standing long jump and single leg hop scores. Okay, that's everything here. So you've got homework this week that relates to doing calculations presented in this PowerPoint and then some other additional questions. Don't forget there is also the follow-up that you need to do for the discussion.